So in one level, this takes one instant of time to get all of these, the n partial products, in this case n equals 4. And then if we would do a parallel add by pairing the n's, then we would have log n levels of parallel adds. But each parallel add, taking log n time itself, would give us log n squared, square of log n, depth of the circuit. But the interesting thing is that you don't need square of log n depth of circuit. You can get log n depth of circuit, even though parallel adds, we proved each parallel add takes log n. Anyone figure out how this might be possible?
Got lots of zeros in there.
Lots of zeros in there, yeah, but that's not the answer because there's a lot of mixing going on. In fact, so I don't think it's the zeros. In fact, I claim that I could do this if I had n, even if I had a problem where I had no zeros here, I could still add up n-bit numbers in log n time. Yeah.
The carry, the carry does not really depend just, I mean, you can think of it as a carry of A, B, and C, or A, B, C, and D, A, I, B, I, C, I, and D, I. I don't know if that helps.
The carry is well, okay, my claim is that if I had actually put in non-zeros and renumbered these so that this would be B1, B0, and so on, that I would actually be able to do it. Let me change that notation then. A7, A6, A5, A4, B7, B6, B0, B7 to B0, and this is BI equals this and xi minus 1, and so on, plus I minus 1. Now, with zeros imagined to the right and the left of the inputs, so Ci y2 xi minus 2 looks like a convolution. Okay, now the claim is that we can also figure out a way to make an adder for 4 numbers that are 8 bits, and they each will, and the total time is going to be still log n. Now, this was something that was invented before the era of divide and conquer. I think the first solutions to this, though, came in the late 50s. So I don't expect that you might be able to do it right online. But the key was to have a redundant representation of numbers, not to so that you carry intermediate results in forms that is not unique, but rather you imagine after you've added 2 numbers that you keep the carries and the other numbers separate, and then you have a way of combining. So you represent every integer in a redundant way. Every integer is now represented as 2 n-bit numbers instead of 1 n-bit number, where there are many ways to represent the same integer. But so then to add, you can imagine adding 2 n-bit numbers together as a process of taking 4 into 2. Taking the 2 for your x and the 2 that represent y, and getting 2 as the sum. If you could, and that can be done with a circuit that requires no carry propagation, so it can be done in constant, some number of levels of logic, 5 levels or whatever. There will be a circuit that'll take 4 inputs into 2. Now, it turns out that, think about it a little bit, you can also take 3 inputs into 2, and it's a lot easier. And there's no reason why you have to even retain the integrity of knowing which numbers you're adding. And so the neat idea is that that we can form a circuit that takes three numbers into two very easily. That's nothing more than a half adder. So xn minus 1, xn yn minus 1, y 0, zn minus 1, z 0, and the sum of those three numbers to be un minus 1, u 0 plus 2 vn plus 2v. So the sum of these three numbers is equal to the sum of those two numbers, where you'd simply say that u sub I equals something and v sub I equals. And what are the formulas for them? Well, u sub I is the number that you get by throwing away carries, so that's xi exclusive or yi exclusive or zi. And vi is the similar thing x plus y plus z div 2, which is the 2 out of 3 function. So that's xi yi or xi zi or yi zi, or all three. Okay, so now those are two, and that's the half-add function that's called h, that's module h, to compute the two outputs u and v as a function of x, y, and z. You'll notice that subscript is always I here in every case. And since it turns out that x plus y plus z, or xi plus y plus zi is equal to ui plus 2 vi, then it's going to be true when you for the whole binary number. These whole n-bit numbers, the sum of these three numbers will be the sum of these two numbers. Okay, you with me on that? So we have a circuit then that takes not too many levels of logic, maybe 2 or 3, to calculate two n-bit numbers from 3. Okay. Now the idea is we're starting out with n.
In general, it should take log n. I mean, if you have n,
Yeah.
n things to add.
Yeah, we got n. So we start out with n things to add together, and we have a way to combine 3 into 2. And now we want to get a circuit with small depth that will add them all together. So we have a way to combine 3 into 2. So what would be a nice way? So I'm going to have to erase something. So I guess I'll erase this now. So let's imagine now that I have a whole bunch of numbers. I'll use capital X1, capital X2, capital X3, capital X4, 5. Let's suppose I had 5 numbers and I wanted to add them together in parallel. 5 binary numbers, and I want to add them together in parallel, and I have a way of combining 3 into 2. So what would be a good idea? Well, I'll take advice from the floor.
You take the first 3 and divide them, and
First 3?
Yeah.
All right.
And you add them together to get 2.
Okay, so I can sort of cancel those out, and I get 2 more, which I can call x6, x7.
Okay, and you just repeat that.
And I can now repeat that and go this way, for example. Take those and then I get x8, x9 from x.
Oh, wait a sec. That's not quite true. Suppose if you had, say, 6 numbers there, then you would, in parallel, you'd take the first 3 and get 2, and the second 3 and get 2. But in this case, the x4 and x5 just go down to the next level.
If I had 6, you would put them into 2.
Yeah.
You can add 0.
Well, yeah, you'd be adding. Okay, and then
Now
you
I
take
have
the
4, so now I have to decide
right.
which 3 to do, and I can take these into 2.
Okay.
Now I have
you've
2
got 3.
left, so those come into 2.
Then you just do a normal addition.
And now I have my parallel addition. Once you get down to 2, then we can't use the 3 to 2 trick anymore. So then we do a parallel addition, which we know we can do in log n time. Yeah. But now, what was wrong with this idea of going
You're not exploiting.
So these 3 were going into these 2, then these 3 were going into these 2, and now I have 3 left, don't I? So that would go into x10, x11. Doesn't that work?
Yeah, it's okay. I looked at that and thought, no, you're not using as much parallelism, because I've seen this method before, but using a tree sort of structure like that. And I knew it worked that way. I don't know, it still seems you're leaving.
If instead of 8 you had 100 or 200 or something like that, essentially you're just reducing one.
We're used to seeing constructions whereby you go from, say, 3 to 1 or 2 to 1. But 3 to 2 is a little bit harder to see what's happening. But in the case of n to 1 or 3 to 1 operation, this method of always combining the 3 at the top and putting at the end is in fact minimum. That's like a Huffman code. If the x's were in somehow ranked in order of size, you taking the largest and putting them into the well, I don't know how to. We're trying to minimize levels, not size here. But you get the fewest levels by this method of take off the left and put onto the right, because the x's occur in order of increasing level, and you're always combining things at the lowest level whenever you can. So if we started out with 9 inputs, for example, then in the first unit of time we would actually do this reduction, 3, 3, 3 into 2, 2, 2, and then we'd have 6, and that would be nice. You could do 3 and 3 again. But even if you don't start out with a multiple of 3, this method is as good as you can do. I believe it can be shown. And the number of levels is what? Asymptotic. N is big. We started with n things. How many levels to this tree? We're going 3 to 2. What?
Log base 3.
Log base 3?
No,
Log base 2 of 3. Yeah, 1.58. Yeah, this is the, this is, you're dividing times log n. Oh, something like that. The way it looks. Okay. Well, we start out with 3 to the k things, then you would expect something like k levels.
Something like K.
Of logic, because we get at every level we get a factor of 2/3, and so that would take, so in k levels we'd get down to 2 to the k. So that isn't quite right now.
Yeah.
So in k levels this takes us down to 2 to the k. So the actual factor is what, t of 3n is equal to more or less, let's solve this recurrence, 1 plus t of 2n.
Yeah, because you're going from 3 to 2.
Because we start out with 3n objects, and then we wind up with 2. After one level, we get 2. We get 2n.
The recurrence you gave works if you're going from 3 to 1. Right.
Okay. So now now the conjecture is that t of n is equal to c times log n, and the question is, what is c? All right. So we're trying to find out what value solves this. So that says that c times log of 3n is supposed to equal 1 plus c times log of 2n. And the log n's cancel. Take off c log n off of both sides of the equation. And so that should be enough to determine c. C is equal to 1 over log 3 minus log 2. Did I do it right? And log 3 is 1.58. Log 2 is, LG is what I should have been using here. Ramsey in the notes. LG is log base 2, because it has only 2 letters. So the log 3 is 1.58 minus log 2 is 1, so that's about 1 over 0.58. number of levels before we get down. And then there's some, what?
You could use natural log there if you wanted to.
You've got that constant, so it doesn't matter.
Because of this, yeah. Yeah, whatever log just as long as I'm consistent, my calculations are okay. In fact, you could use the log base C, or sorry, log base 1 over C, and then make it equal to 1. Yeah. Time? Oh, okay. 2-minute warning. So, all right. So that's what this circuit does for the multiplier. Let's go back to that.
Incidentally,
What? Yeah.
log to base 1.5 would probably work pretty easily. I mean, if you just put it in there,
Log to base
1.5.
base 3/2, because this is log of 3/2. So C is
no, I was just
so C
looking
is
at
1
it.
over log of 3/2, and therefore this is log n over log 3. So it is equal to. So this is equal to log 1.5 of n.
Because every time the number just reduces from 3 to 2. So
That's a good. Yeah, that's it. So it's 1. Yeah, 3/2 is indeed the base of the logs there. Good. Now, so the final thing is that this multiplier circuit it consists of 2 8-bit numbers, and as I say, worthwhile to generalize to 2 k-bit numbers, where k equals 3 when you're testing. And first of all, we just form the 1-bit products by taking and. Sorry, that's what the multiply. This is the B module, which is a multiply byte by a bit and shift. Then we do these R, which is a reduction of 3 inputs to 2 inputs. And so I use a double subscript notation there. But it's exactly what like we wrote on the board. So we start out with the first subscript 0, 1, 2, and we, I guess initially we had 0 to 7. So then when I is 0, 3i plus 1, 3i plus 2 is just 0, 1, 2. 2i plus 8, 2i plus 9 is equal to 8, 9. And so you're getting new inputs called x8 and x9, say. Then we're going to add. At the next pulse, we're going to add 3, 4, 5, and call those 10 and 11, and so on for I equals 0 to 5. And then finally, the 2 things that are left are going to be 18 and 19, and we use the parallel adder, and that's the result of the multiplication. So this is a circuit that takes 16 input. It gives us a total of 65,000 possible inputs, and for each of these, we're supposed to compute the correct 16 bits of output, and when all is put together, you should get that many gates. So the first thing to do is write a little program that converts, that builds an internal computer representation of the circuit, and verify that you do in fact get 401 gates. All right, and so I'll see you all on Thursday for the last go around on cryptography. Also, you remember, well commented and programs accompanied by a write-up are due for your feedback from the friendly TA. Just performing on TV was not the end of that problem. You're also supposed to turn in your conclusions and explain what you did and why. Okay.
Is it due when? Thursday?
I thought they were due today, but they are. Yeah.
Well, our friendly TA.
Yes. Okay.